Okay, so we're done with chapter 2 and moving on to integration now. So similarly to what we've done before, we're going to try to build up a proper definition of the integral that we can use and then try to rigorously prove things about the integral. Okay, so you have some sort of intuition for what an integral is, right? Think of it as being the area under the curve that we're trying to compute. So we've got our function, whatever it is, from a to b. And we're trying to come up with some sort of meaningful value for the area under this curve. Let's try to approximate or define the area under the curve. Okay, so when we were doing derivatives, right, we said we have a curve that's complicated. We want to instead bring this down to the problem of something that involves something simple, like a straight line. So we essentially reduced the derivative to let's draw a straight line and know how to find the slope of a straight line, and took limits in an appropriate way to get our derivative. Okay, we want to do a similar kind of thing here. We want to come up with some sort of simple object, simple function that we could easily define the area under and try to use that to build up our integral. So a simple function here to find the area under, presumably the simplest thing you can come up with is just a constant function, right? So we want to use extremely simple functions. For example, constant functions to build up the definition. Constant functions are easy, then we're just find the area of a rectangle. Now, one constant function is not going to do it, right? Because one constant function is not going to capture all the behavior of this thing. It's not like the derivative. The derivative, we were just interested in the derivative at a point, so we just needed one straight line. Here, we're interested in the behavior throughout this interval, so we're going to need lots of constant functions. So our game is going to be, let's try to approximate this thing not by a straight line, not by a constant function, but by a piecewise constant function. We're going to break it down and use lots of little rectangles and add up the area. So let's try to approximate f by something that is piecewise constant. Right, so I might have one value of a constant here, one value of a constant here, one here, one here, one here. And each of those constant functions in the little intervals, I can easily find the area of. Okay, so I need to start, before I do anything else, I need to start by breaking up my interval, a to b, into some smaller subintervals that are going to form the base of all these little rectangles. So first step, let's split up the interval a to b into smaller subintervals. All right, we're going to give this a name. We're going to call this a partition of the interval when we break it up like this. So here is going to be the precise definition of the partition of the way we break up this interval. A partition P of the interval a to b. Okay, it's going to consist of a collection of points. The points that form the endpoints of all of these bases of the rectangles. Okay, so this is a finite set of points. All right, that's important also. We only want to add up finitely many of these at a time. So I'm going to call this one x0, x1, x2, all the way down to xn. N is some number. Okay, so x0, which is equal to a, it should be less than x1, should be less than x2, all the way down to less than xn, which is b. So we have our collection of points, and then we want to have some concept of how well these points are actually resolving these intervals. We expect, just like when we took derivatives, we had to sort of take a limit as we got arbitrarily close to x0. We're going to expect we're going to need some sort of limit as we let these things get arbitrarily narrow. So we need some sort of number that tells us how narrow are these rectangles sort of overall. They might be different. They're not necessarily all the same width. But what's a good ballpark that says they're all getting smaller or they're not getting smaller? Yeah, delta x, but delta x may be different across all of these. So what we're going to care about is that each one of these delta x's is getting arbitrarily small in the limit. We'll need that limit. So what we're going to look at is the largest delta x. And if the largest possible delta x is going to 0, everything goes to 0. We're going to call this the norm of the partition. So the largest length of all subintervals is the norm, which we denote by this of the partition. And I'll write out it not in words as well, the norm of the partition. Okay, so the norm of P is going to be the maximum, okay, of all possible xi minus 1, where I is going to go from 1 to n. Okay, the maximum is well defined because we're just taking the maximum of finitely many things. So that's not a problem. If our partition was something like this, so here's x0, here's x1, here's x2, here's x3, x4, x5 equals b. Then for the norm, we'd look at the largest one of these. And this length here would be the norm of P. Okay, so that's a partition. Now we're going to expect one partition. If I just pick this partition and create some rectangles on it, I'll get a number, but it might not be the number that I want. And it's the number that's sort of a reasonable definition of the area under this curve. We're going to have to look at different partitions, what happens as we refine, as we add in more points, more nodes. Okay, so this is the concept of a refinement of a partition. So we're going to say that if P and Q are two partitions of the same interval, okay, and if one of them is a subset of the other one, so what do I mean, one of them being a subset of the other one? That means if P is a subset of Q, so if this is P, and then I have Q here, if P is a subset of Q, that means everything in P is also in Q. So all these points are also in Q. But then there may be other points that are also in Q. So Q may also include this point and this point and this point. Right? So Q contains everything in P plus more. We've added more points. We've potentially reduced the size of the norm of Q. Then we're going to say that Q is a refinement.
Why not a strict subset?
What's that?
Why not a strict subset?
It could also be a strict subset. Sure.
Because if they're equal, is it still a refinement?
Trivially, yeah. Not in an interesting way.
Gotcha.
What's that?
What do you mean by
Well, he was asking why I didn't write it like this. Okay, so we've got our nodes. Then let me draw a picture of my function again. So I've got some function, and I've picked some nodes. So this is x0, this is x1, x2, x3, x4. So I know the base of each of my rectangles that I'm going to use. Now I also have to come up with some sort of height for each of my rectangles. And there are lots of potential options that I could use for my height. But presumably we want to build the function value itself into it, right? I'm not going to pick something up here to be my height, because that's not reasonable. We want to look at what the function's doing. So in order to pick the height, maybe I'll get a different color pen. In order to pick the height, what I'm going to do is just pick any one value in each interval. So I might decide right here, this is going to be a value that I pick, maybe C1. And then I'm going to say, let's look at the function value here at C1. And that's going to be my height. So here, this is f of C1. And I'm going to draw this rectangle. And I go to the next interval, and I need to pick a point in here too. I'm just going to pick one. Maybe I decide to pick this point over here. Maybe later we'll think that there's clever ways to do something. It's not always obvious. And again, I go up and I say, what's the function value there? That's here. Here's f of C2. And that's going to become the height of my rectangle. Okay, and do the same thing in every other subinterval. So I pick a C3, climb up to here. That becomes the height of my rectangle. And I pick a C4, and that becomes the height of my rectangle. Okay, so for each subinterval, what have we done? We choose any value, ci, that lives between xi minus 1 and xi. Okay, so C1 could have been any of these guys. And approximate the area over this subinterval using a rectangle, using these rectangles that I've drawn here. So using a rectangle of height f of ci and base xi minus 1. Okay, so of height f of ci and base xi minus 1. And then I add up all of the areas of all these individual rectangles, and I get some number, which may be close to our target number. Maybe it's not. Don't know yet. But whatever number we come up with, we're going to say this is a Riemann sum of f over this particular partition. Okay, so this is the definition of a Riemann sum. So let's let sigma equal the sum over all of these little subintervals of f of ci times xi minus xi minus 1. Okay, where? Let's put everything in the definition. Okay, so these x's come from a partition of my interval. So p equals x naught, x1, up to xn is a partition of the interval. Okay, and ci is just any point that lives inside of the ith interval. Could be the left endpoint, the right endpoint, the midpoint, somewhere in between, doesn't matter. So ci belongs to xi minus 1, xi, and this gives a number. Okay, any number that can be written in this form, we're going to call a Riemann sum. So we say that sigma is a Riemann sum of f, of the function f, over the partition P. Okay, so this is just a number, right? There's lots of ways of writing out these Riemann sums. I could do it in very dumb ways. I mean, I could do the simplest partition I could think of would just be these two endpoints, right? One rectangle. That's going to give a number. It might not be a number close to what I want, but it's a number. There's lots of different ways of coming up with these numbers. So now the question is, how do I use this concept of a Riemann sum to build a definition, a reasonable definition of the integral? What do I need to happen? So I need, in some sense, to make delta x go to 0. Okay, delta x, right? Each of these delta x's is different. What I need is to make the norm of the partition go to 0, right? So that of all these subintervals, each one of them is going to 0. The biggest one goes to 0. That means the little ones go to 0. So indeed, we need to take some kind of limit. So we know how to write down limits. So now we're just going to try to use that concept that we want norm of p going to 0. And we're hoping that as norm of p goes to 0, these things, these Riemann sums, approach some value, right? They should approach a limit. If they don't, if as the norm of p gets smaller and smaller, we can make these values do whatever we want, then this is not a good sign for our function. Okay, so we're going to say that f is Riemann integrable on the interval a to b if, okay, so we know that we want these things to approach some limiting value. So there's some number that those things approach. I'm going to call that number L, the value of my limit. So if there exists some L belonging to a set of real numbers such that, okay, and now we just have to start writing down what it means for this to converge to a limit. So what it means for it to converge to a limit, that for every epsilon greater than 0, right, there should exist some delta greater than 0. Okay, and now what I'm going to ask, the delta, right? Delta is the thing that we're taking to 0, which is the partition size in this case. Now, for a given partition size, there are many, many partitions that have that size, right? If my partition size is this width, then I could do this and this and this, this and this and a bunch of these. I could put this and this and then 10 million other things in here, right? Those would all have the same partition size. So I'm going to say that if P is any partition of AB, with my only constraint being that the norm of P is less than delta. Okay, so I'm not saying that I'm looking at left endpoints or right endpoints or mid endpoints. I'm saying this has to work no matter where I pick my C's, as long as these things are sufficiently close together. Then you know the conclusion. These sigmas are supposed to approach L. So we're going to say that sigma minus L should be less than epsilon, right? Where sigma is any Riemann sum of F over P.
Question.
Yes.
As the size of the partition goes to 0,
Yes.
do we assume, is it implied that the number of partitions increases to infinity?
So yes, so as the size of the partition goes to 0, we're going to need the number of points to also go to infinity. That's going to be the only way. If I say, I'm requiring my partition size to be less than 10 to the minus 10, that means I'm going to require a lot of points to get there.
Right.
And if I want my partition to be even smaller, more refined, then I'm going to need even more points to get there. So absolutely.
When we read P is any and sigma is any,
Yes.
that's like for all, effectively, right?
It's like for all, yeah. So for all possible partitions with P less than delta, so it could be a partition, it could be where we have an equal spacing that's delta or just under delta. It could be where I have one spacing that's delta and the rest are all 10 to the minus 10. Those would both have the same partition size. And we have to look at all of them, and we have to be willing to look at, again, for all possible choices of these C's.
So if we were to find some partition with some Riemann sum
Yep.
that no longer satisfies the epsilon part,
Right.
that we've said that it's not Riemann integrable.
That's right. So if we can find one partition, just again, when you're trying to prove something's true, you have to prove it for everything. When you're trying to say this statement is false, you just need one counterexample. So if I can find just one particular partition that breaks this, then I'm done.
That would imply that the function is not.
Then it would imply that the function is not Riemann integrable.
But does that imply there's anything about continuity?
Does that imply anything about continuity? We'll come back to that. Probably not today, maybe next week. But yeah, there are some connections between continuity and integrability. No, it's clear. Hopefully it's clear from even this diagram. We're not assuming the function is continuous in order to be able to integrate it, because I'm actually approximating it by something that is not continuous, right? So piecewise constant function is not continuous, and we're using that as the basis for our definition. So we better be able to handle some non-continuous functions. But yeah, it turns out continuous functions are integrable. All right, so then we're going to write, this you already know, just doing it to be complete, the integral from a to b of f of x dx is equal to L. Any other questions on the definition before we start doing some examples? Okay, so we'll do one or two examples of how to use this definition to compute the integral. Like anything, using the definition directly is a lot of work, right? So you'll want to figure out how it works, understand how it works. You need the definition to prove things about integrals. But then we'll also want to use the definition to build up rules for how to do things more easily. Okay, so here's an example. Let's use Riemann sums to compute this integral. Integral from a to b of x dx. Okay, and what our goal is we've got to find some number L such that we can satisfy this definition. These proofs, or these exercises, start the way our old exercises with limits and stuff started, because what we're really doing, it comes down to we're doing a limit problem. So we need an epsilon. Okay, and then we need to start looking at general partitions. So let's consider partitions P of the interval a to b with the norm of P is less than some delta, but we don't know yet what delta is supposed to be. So I'm going to say with delta to be determined. Okay, so we've picked our epsilon, our tolerance. We're going to construct a very general Riemann sum, where at this point we haven't put any constraints on the partition, or we're not really putting any constraints on where we pick C. We're just going to try to build a very general Riemann sum and then see what conditions do we need to put on that Riemann sum in order to pull this off for some number L. Okay, so let's write down the general Riemann sum. So a very general Riemann sum of F over P is okay, so again, we got to add up over all of these little intervals that we've created. Okay, so we're going to put f of Cj. Here, f is equal to x, so this is just Cj. Times xj minus xj minus 1. Okay, and again, where these c's live in the little subinterval. Okay, so the goal of this, again, C could be anything, right? It's anything that lives in this interval. So we want to obviously try to simplify this a little bit in order to extract a reasonable candidate for L. In the simplification, we don't hope to evaluate this exactly. What I hope to do is try to organize it in such a way so that I have one term that looks like kind of the bulk of what's going on, that could serve as my candidate for L, and another term that looks like the leftover, something that's hopefully small, something that hopefully depends on the norm of the partition, right? And that will go to 0 as I take my partition size to 0. So we're going to try to rearrange this. So we need some kind of estimates on this. So what I'm going to do is just try to break C up a little bit. Okay, so here's my xj minus 1. Here's my xj. And what I want to do is find sort of a dominant part of my function and whatever is left over. So if you were going to pick any Cj in here, if you got to pick, you didn't get to pick, but if I was going to give you the choice to pick, where would you pick it, probably? The middle. That would seem reasonable. So we're going to try to write it that way. It would be nice if Cj lives here. It doesn't. But maybe we can approximate this by what happens in the middle. And there'll be some error, and we have to keep track of that. We don't have to know exactly what the error is, but we have to be able to bound it. We have to be able to say the error stays small. So in the middle. So in other words, I'm going to say my actual Cj is over here. What I'm going to do is write it in two parts. I'm going to write it as the sum of the midpoint plus some error. So let's write Cj as the midpoint of these two things, so xj minus 1 plus xj over 2 plus some error. Okay, this width here is going to, sorry, that's the wrong width. This distance here from the midpoint to C is going to be my error. All right, the nice thing being that this has a lot of structure, right? Now I know exactly where this point lives in each subinterval, which means I have some hope of doing these sums. And this dj is definitely small. What's the biggest dj could be? It's the half of the interval size, exactly. So here we're going to have that dj is less than or equal to xj minus 1 over 2. And I can maybe do one better than that, right? We have lots of these intervals to do. I've just drawn one of them, but there's a bunch of them. But yeah, you have
Bounded by half the norm of p.
it's bounded by half the norm of p, exactly, right? So each one of these intervals is less than the norm of the partition, right? Because the partition size was equal to the biggest size of these intervals. This might be the biggest size of the interval, or it might be smaller than the biggest interval, but certainly in any case less than the norm of p. So we're going to write that this is less than the norm of p. Right, so again, we don't know exactly what things are. We're never going to write down the error exactly, but as long as we can keep it under control, we've got a handle on how bad our estimate is, we can carry that through. Okay, so let's go back to our Riemann sum and see if we can do some estimates on this sum.
xj minus xj minus 1 is one partition.
Xj minus xj minus 1, yeah, xj minus 1 to xj is one subinterval. It's one part of the partition.
And we're assuming that's inside the interval A to B.
It's inside the interval a to b, yes. Right, that's the definition of a partition, is that it starts at A, it ends at B. And there's potentially other points, finitely many other points in between. Okay, so let's go back to our Riemann sum. So the Riemann sum was sigma j equals 1 to n. Now we had this cj, and now we've written cj in a different way, right? We've written in terms of the midpoint plus the error we made. So this is xj minus 1 plus xj over 2 plus dj times, so that's our height, and this is our base. Now what I want to do is break this up. Again, our goal is to find a candidate for L. What is kind of big picture what's going on here? And then we'll have some leftover error that we can keep under control. Okay? So what I want to do is split this up into two pieces. One that has the bulk again, and one probably that involves these d's. That is an error term, but it's an error term that we have some ability to control and to bound. So if I break this up, what am I going to get? A half. I'm going to multiply this times this. So what do I get? Xj squared minus xj minus 1 squared. Plus another term that involves these errors. Okay, so dj xj minus xj minus 1. All right. What does this sum to? There's a trick. So you don't need any fancy rules or laws. right? So this is a telescoping, right? So what do I have here? I have xn squared minus xn minus 1 squared plus xn minus 1 squared minus xn minus 2 squared, right? There's going to be cancellation all the way through. So this guy telescopes, which means if we want to sum them up, all I need is the biggest of these and smallest of these. So this is going to be half xn squared minus x naught squared. And then I still have this term. All right. Does this number depend on my partition? Right? No, it doesn't, because we always said xn is always b. It's always the right endpoint. X naught is always a. It's always the left endpoint. So this value here is equal to half b squared minus a squared, which does not depend on the partition. That's good. We want to come up with some sort of bulk piece of this that doesn't depend on the partition, because we're looking for a candidate for the limit. We're looking for a candidate for L, and L is not allowed to depend on which partition we use. L is just the final value of the limit. So this is potentially a candidate for L. Whereas if we look at this thing, okay, these guys, I don't know exactly what this is. I have no hope of knowing exactly what this is. But I have bounds on this, right? I know that these guys are small, and I know that these guys are small. So this term is unknown, but we can bound it. Okay, so again, I'm proposing this as a good candidate for L. We haven't proved yet that this is the value of the integral, but it looks like a reasonable choice. So I propose L to equal 1/2 b squared minus a squared. Okay, what do we need to look at? So we're trying to finish a problem that, right, we have a definition that really is just a definition of a particular limit. So we know whenever we're doing the definition of a limit, what we need to write down is the thing we're taking a limit of, which in this case is sigma, minus our candidate value of the limit. And we want to try to force this to be less than epsilon. Epsilon was the tolerance we chose right at the beginning. Okay, so sigma minus L is going to be equal to this guy here. Okay, so the sum j equals 1 to n of dj xj minus xj minus 1. All right, we're going to try to bound this, try to get this less than epsilon. We have one of our favorite standard tools, which is the triangle inequality, right? Which is I can bring the absolute values inside the sum. So this is going to be j equals 1 to n of the absolute value of dj times the absolute value of xj minus xj minus 1, which is, this term is always positive. And the good news is we know something about this. We found bounds on this terms before. It's less than or equal to half the partition size, exactly. So this is less than half the norm of p times j equals 1 to n xj minus xj minus 1. All right, what does this sum to? B minus A, yeah, right? Again, two ways to think about it. One is that it telescopes. The other way to think about it is that we're just adding up the width of all of our subintervals, and they better add up to give us the entire interval. So this is 1/2 times the partition norm times B minus A. Hey, can we make this less than epsilon? Sure we can, right? As long as the partition size is small enough, right? We're not asking for any particular choice of partition, or that it be uniform, or that points be chosen in a particular place, or the C's be chosen in a particular place. All we're going to ask is that the norm is small enough. So indeed, we can make this less than epsilon as long as the norm of P is less than 2 epsilon divided by B minus A. And this becomes our good candidate for our delta. Right? And that's it. That's how, again, we're effectively just doing a limit problem here. This is how we conclude our limit problems. We started with an epsilon. We said we look at the thing we're taking the limit of minus the value of the limit, an absolute value. And we say, can we make it less than epsilon? And as long as we find a delta that accomplishes that, we've done it. And we've verified the definition of the limit. So we can conclude by saying, great, this worked. The integral from a to b of x dx, we found a value. The definition is satisfied as long as we choose this value of L, is equal to 1/2 b squared minus a squared. Which means that your calculus professors did not lie to you when they taught you this rule for this. But in case you've been worried about that for the last couple years, now you can feel confident. We can integrate linear functions. Any questions on that example? Okay, are all functions integrable? No. Why not? Well, we can have, right, we started with these piecewise constant functions which were not continuous. We could integrate those. Well, maybe, maybe not. We haven't proved that yet.
Stuff like the impulse function isn't Riemann integrable, right?
Well, an impulse function, if you're thinking of like a delta type function, then that's not actually a function. So
Also true.
it's a convenient lie that we tell ourselves.
All I know is this function, like we can't analytically like.
Sure.
But I don't know if this
Right.
function is numerically like.
Right. Right. So e to the x squared you threw out. That's Riemann integrable.
It's just not analytic.
You just don't have a simple form for it. All right. So in fact, not everything is integrable. And not using this definition. So when I wrote down the definition of integrable, I actually wrote down Riemann integrable. So throughout the semester, I'm going to drop the word Riemann most of the time and just say integrable, but I'm just going to throw out there's other ways of defining the integral, and some of them are more powerful than others. So I'm going to do an example of a function here that's not integrable using this definition, but you can integrate it if you use a more powerful definition. You need some measure theory for that. So here is a somewhat pathological example. And then we'll also do less pathological examples where you also can't do this. But this one's kind of fun. So let's let g of x be equal to 1 if x is a rational number, and 0 if x is irrational. And we'll define it on the interval from 0 to 1. So this is a legit function, right? Any point between 0 and 1 I can plug in and it will spit out a number. But it's going to be bouncing around like crazy between 1 and 0. So here our problem is to show that G is not Riemann integrable. Yeah.
Out of curiosity, what is the value of the integral? Would it be 0?
The value of the integral is 0, yes. But not using this definition.
Yeah, no.
Using this definition, there is no value. But yeah, if you do some measure theory, you learn the Lebesgue integral, it's 0, which comes down to the fact that there's a lot more irrational numbers than rationals. That's right. There's infinitely many of both, but there's more of these than these. Measure theory is fun this way. All right, so let's try to break this thing. So we're trying to break the definition. So that means, all right, the definition says for all epsilon, something happens. We're trying to break it, so that means we just need to find one epsilon that doesn't work. So I'm going to try epsilon equals 1/2. Okay, and I'm going to let P be any partition. The norm of P can be as small as you like it to be. I don't care. No matter how small it is, we're going to try to show that we cannot get this Riemann sum to stay within a value of 1/2 of any choice of L. All right, so we're going to need some Riemann sums to do this. So in each interval, xj minus 1 to xj, okay, we typically chose a cj. What I'm going to do is actually pick 2 points, a cj and a dj. And what I'm going to try to do is construct 2 Riemann sums and show that those Riemann sums, no matter how small the partition is, those Riemann sums are too far apart. Right? We know that if the partition is small enough and if this function is integrable, then it shouldn't matter where I choose my c's. We should get values close together. I'm going to show actually I can get values that are far apart. So let's choose, we can find cj and dj such that one of them is a rational number, one of them is not a rational number. cj is rational and dj is irrational. And then we write down 2 different Riemann sums. So one Riemann sum involves the c's. Sigma 1 equals the sum of, okay, g of cj, xj minus xj minus 1. All right, what is g of cj?
0.
So cj is rational, so it's 1. Yeah. All right, so this is the sum of all these subintervals. We've seen this before. B minus a, which is 1 minus 0 in this case. So that's one choice of Riemann sum. Okay, and sigma 2 is going to be another Riemann sum. Okay, this time I'll use the d's. And what is this Riemann sum equal to? 0, right? All of these values of g are 0, so So the sum is 0. Okay, so what does that mean? It means I don't care how you've picked L, right? For any choice of L, either we're going to have sigma 1 minus L is bigger than or equal to a half, or sigma 2 minus L is bigger than or equal to a half. Right? Sigma 2 is down here at 0. And sigma 1 is up here at 1. And if L is some value in between them, at least one of these intervals is going to be bigger than a half. Right? L may be down here close to 0. If it's close to 0, then it's not close to 1. If it's close to 1, then it's not close to 0. Okay, so in other words, what does that mean? Okay, so for every L and for every partition, no matter how refined, right? I don't care if you take your interval and you break it up into like a googolplex of equally spaced points. We can still do this. Okay, we can find a Riemann sum of f over p such that sigma minus L is bigger than or equal to a half, which we chose to be our epsilon. And that is precisely the opposite of our definition of Riemann integrability. We've broken it, right? We cannot find any value of L that makes the definition work, so we say G must not be Riemann integrable. Any questions on that? It always feels a little difficult, or a little different, sometimes a little more difficult, not trying to satisfy the definition, but to break it. Yeah.
Is D the same D as the error?
This is a different D than the error. Different problem, different D. Yeah. So I'll just put a note here. We actually did this calculation at the end of 481 last year. We had some time left over, and we actually worked this out. If you use the Lebesgue integral instead of the Riemann integral, we get that the integral is 0. This ends up being what in the world of Lebesgue integration, this function ends up being what's classified as a simple function, the kind of function that we use as our building blocks, just like piecewise constants were in this case. So that is a slightly pathological example of why we cannot integrate every function. We can have some less pathological examples as well. Are there any last questions on this one, though? Okay, so let's do something that maybe you're a little more likely to see. What happens if you have a function on AB that's unbounded? It either diverges or converges. Okay, so we haven't started thinking of, you're thinking of improper integrals, right, where you say, I leave out the endpoint and take the limit as we go to the endpoint. So yes, sometimes we can do this using improper integrals. If you want to straight out use the definition of the Riemann integral, I take my interval, I break it up to subintervals, I use this definition. It turns out you cannot do that with unbounded functions. You need to carefully define this in terms of other limits. So this is a theorem. If f is unbounded on AB, then f is not Riemann integrable. It doesn't have to be an open interval. So I could have a function that's defined everywhere but can be arbitrarily large. So I mean, I could have something like, say, 1 over x when x is not equal to 0, and then I just define it to be 0 when x is equal to 0, right? I can plug holes. But right now, if we're working on the definition of the Riemann integral, the definition of the Riemann integral only works on these closed intervals because we have partitions and we need to include the endpoints in our partitions. Okay, so this is another example of trying to break the definition. So we're going to reason in a similar way to what we just did. This one's actually a little more work because we don't have a concrete function in front of us. Even though the last function was bizarre, it was easy to work with because it was either 1 or 0. Okay, so again, let's let P be any partition of AB. And I want to do what I did here. I want to show that no matter what partition I use, no matter how refined it is, I can come up with 2 different Riemann sums that give me dramatically different values. So I'm going to ask these difference between these values to be some number m. Okay, so let m bigger than 0 be a fixed number. So this is our goal. We'll say our goal up front. Our goal is to do exactly what we did back here. Come up with 2 Riemann sums on P, no matter what P is, that are different from each other by this amount m. And no matter how tiny I take my partition size to be, they just keep being different than each other by this amount m. So let's construct Riemann sums, sigma 1 and sigma 2, such that sigma 1 minus sigma 2 is bigger than or equal to m, no matter how small the norm of P is. We're trying to say we can always do this. For any partition, we can find things that are this far apart, this fixed amount far apart. Maybe m is equal to 1 or something like that. Okay, so again, I'm going to need some CJs and I'm going to need some DJs, right? Just like we did in the last example. All right, I don't have any super clever way to start picking them like I did last time. Last time it was obvious, pick the C's so they get 1s and pick the D's so you get 0, or the other way around, whatever it was. I don't have anything that clever here, so I'm going to start by saying, let's just choose any C's. Okay, and that gives us a Riemann sum. Okay, so sigma 1 is just going to be standard Riemann sum, f of Cj, xj minus xj minus 1. Yes? Thank you. This should be xj minus 1, xj. Now I need to try to construct a second Riemann sum, and it needs to have a very different value from this Riemann sum. And I need to use the tools at my disposal. What tools or information are at my disposal? The fact that f is unbounded. So we're going to try to use the fact that f is unbounded, that I can always make f as big as I like, in order to construct another Riemann sum that's really different from this one. Okay? So we need to build another Riemann sum. Okay, that differs from this. By an amount m. Or more. Okay, so how are we going to do this? Let's draw another picture. So f, I'm not really sure what f does, but it gets really big at some point. And we got to use the fact that, in some of these little subintervals, I'm going to get CJs and DJs that give me practically the same value, and there's nothing I can do about that. But at least at one point, I should be able to find a subinterval where I can get very different values. So this is what I need to try to do. I need to find maybe my CJ is here, and maybe my, let's call this f of CJ, and maybe my f of DJ is way up here. Right? I only need to do that once as long as I make these values far enough apart. Again, subintervals, I'm not going to be able to make those values far apart. So I need to find a point DJ where f of DJ is much different from f of CJ. Yeah.
Can say that for any partition P, there's at least one subinterval that's unbounded as well.
There's one. What do you mean by one subinterval is unbounded? Well, there's one subinterval where f is unbounded, exactly. And we need that. All right, so how much different should these be? Well, we need an m popping up somewhere. But we know that then that's going to get multiplied by an xi minus 1. So we should have a difference of at least m divided by xj minus xj minus 1. Because we know that this difference is going to get multiplied by the width of the rectangle, which is small. We still want an m popping out. Okay, so we need the fact that f is unbounded. That's the only information we've got, right? If I don't have any other information about the function, there's no way I can prove that f is not Riemann integrable, because we know some functions are. So since f is unbounded, what does it mean for a function to be unbounded?
As you approach a certain number, the limit approaches infinity.
So does the limit approach infinity? Maybe. There's a precise definition.
Given any x value in the interval, you can find another x value such that f of x2 is bigger than f of x1.
Okay, so you can always find a value where f of x2 is bigger than f of x1. Okay. There's still a more precise definition of unbounded. Yeah.
You can choose any number such that as you approach the limit, f will always be bigger.
Okay, so we can choose a number, any number you like, however big you like. No matter how big you choose that, I can always find a point x where f gets bigger than that number. Exactly. So since f is unbounded, we can find some value, some point C in AB. I'm not sure what point that is. such that f of c in magnitude, I'm not sure whether this is unbounded from above or below, so we'll just take the absolute value, is bigger than or equal to the maximum of all of these f of cj plus m over xj minus 1. Right, so I'm looking for a point that is bigger than f of cj by at least this amount. I'm not sure which interval this point is going to live in, so I'm going to require it to be bigger than what this does in every possible interval. So I'll look at this value in every possible interval. Again, some of these may have f's that are very small. Some of these may have f's that are very large. I'm not sure. But we can take the maximum because we're just taking a maximum over a finite collection of subintervals. And then I can say that's a number, it's some number. It might be a very large number because we might have picked f up here and somewhere. But however large this number is, I can find a point where f gets even bigger. All right, this point lives between a and b. That means it lives in one of these little subintervals, right? It has to live in one of them. So we're going to say c lives in xi minus 1 to xi for some choice of I. Okay, so over here, this is going to be my xi minus 1, and this is going to be my xi. And maybe this is where I chose my c. Okay, so we're trying to come up with a second Riemann sum that's really different. I don't want to muck with things too much because I want it to be simple to do the estimates. So let's define my DJs now. And I'm going to mostly let them just be the same as the CJs because, again, I want these things to be easy to compare to each other. So I'm going to mostly let these be CJ as long as j is not equal to I. But at this one special point, in this one special subinterval, where I found a c that makes f enormous, I'm going to change it. And I'm going to let this be c if j is equal to I. Okay, so I had C0, C1, C2, C3, C4, and now I'm going to have D0, D1, maybe D3 got moved, and D4 stays the same. So I've just moved one point over to ensure that my f gets really, really, really big at this point, much, much bigger than it gets anywhere else. Okay, and now we can write down a second Riemann sum. So a second Riemann sum of f over the same partition. So we're still using the same partition, right? x0, x1, x2, up to xn are all the same points. All I've done is I've moved the CJs in between those intervals. In fact, I've only moved one of the CJs. Is sigma 2, which is j equals 1 to n, f of dj, xj minus xj minus 1. These are almost all the same as what I had before, right? Except at one point. So we're going to try to rearrange this a little bit. Let's compare it to f at cj. Now, what have I done? Most of these terms are the same, except at one point I, so I better subtract that point off and put in the correct thing. So I'm going to have minus f of ci, xi minus 1, because that was wrong. And what I actually need to use is f of this value. Oops. Let's put the correct difference here.
Simplifies to F and C.
Well, almost. So what is this sum here? That's sigma 1. That was the first Riemann sum. So this is sigma 1 plus f of c minus f of ci times xi minus 1. So we've got two Riemann sums. And what was our goal? Our goal was to show that these two Riemann sums could be made quite far apart in value. And now we're in business to actually compare their values, because we can write down explicitly the difference between them. Okay, so if we look at the difference, sigma 2 minus sigma 1 is going to be f of c minus f of ci times xi minus xi minus 1. Now this we picked really carefully, right? We chose C so that this would be very much bigger than f of ci. So this, let me break this up carefully. This is going to be bigger than the absolute value of f of c minus the absolute value of f of ci times xi minus xi minus 1. That's triangle inequality with a twist. I'll write that. Oh, it makes a good exercise to try to prove that. It's basically a one-line proof from the triangle inequality, but you have to set it up cleverly. This we know is much, much, much bigger than this. This is bigger than m over xi minus xi minus 1 times xi minus xi minus 1. Which is m. Any questions on this so far? So now we're there, right? Our goal was to say that no matter how tiny this partition is, no matter how much we refine it, we can always find two Riemann sums that are different from each other by an amount m that's fixed. And that means it's the same picture that we had before. So here's sigma 1, here's sigma 2, right? There's no way I can choose an L that stays within epsilon of all possible Riemann sums, right? It's going to differ from one of these. So there's no way to choose L such that sigma minus L is less than epsilon if epsilon is less than m for all possible Riemann sums. Right? Because if L is down here close to sigma 2, then sigma 1 minus L is huge. I can't make it less than m. If L lives up here, then sigma 2 minus L is going to be huge. I can't make it less than m. Yeah?
Should it be m over 2?
Should it be m over 2? Where's an m over 2?
Like instead of m there. Because you could pick the midpoint
Less than m over 2, sure. So this is exactly what we did before. We looked at the definition of Riemann integrability, which is some limit that you have to come up with, and we showed that we could break it. We showed that for some possible choice of epsilon, with this choice of epsilon, I don't care how small your delta is. You make it as small as you like. You make your partitions as refined as you like. We still can't get this difference to be less than epsilon. We can still find Riemann sums that break it. So we can conclude F is not Riemann integrable. So that means anytime I give you an unbounded function, if I give you f equals 1 over x, and maybe I plug the hole so that it's defined everywhere, and ask you to integrate it on 0 to 1, you can come right back at me and say, that's impossible, right? I have a theorem that says it's impossible. Anytime you're trying to prove a theorem about a Riemann integral function, you can assume the function is bounded automatically. So if I say, prove that Riemann integral functions have this property, you're allowed to assume they're bounded, because they are. Any questions there? Okay, so we've been talking about very general partitions, right? And very general choices of our C's. So where we're going to head from here is to say, do we always really need to do everything in the most generality? Of course, we start with a definition that makes sense, but then we try to build rules that are a lot easier to work with in practice. So that's where we're going to be headed from here. Next class is let's try to work with simpler partitions, and we might be able to do a lot with simpler partitions.